Hi, I'm Shahnawaz. This is the first course on algebraic topology. Now, in algebraic topology, we study the relationship between topological structures and algebraic structures. And so we go from topology to algebra. In topology, we mainly deal with topological spaces and homeomorphisms. And in algebra, we deal with groups and isomorphisms. Now what we do here, we associate a group with a topological space and translate the underlying homeomorphisms with the associated isomorphisms equipped on the group. In this interplay, if two topological spaces are homeomorphic, then the associated groups are isomorphic. But here we don't consider topological spaces up to homeomorphic, but we consider topological spaces which are up to homotopic. Now what is a homotopy? That we are going to study ahead. A homeomorphism is actually a continuous map between two topological spaces. Suppose we have a topological space X and a topological space Y, then a map F is said to be a homeomorphism if F is continuous together with its inverse, and F has to be bijective. Then we say that this F is a homeomorphism. Here we don't consider spaces up to homeomorphism, but the space is up to homotopy. For example, if we consider a unit district, say this is our closed unit district D2, and let us consider another space, a closed interval I. Now these two objects, they are not homeomorphic because there exists no continuous map F from D2 to I which is continuous with its inverse and which is bijective. There is no such continuous map from D2 to I such that this inverse map is also continuous. However, these two objects, they are homotopic. Now we'll move to define the homotopy. So let us consider two topological spaces X and Y. Let X and Y be topological spaces. And F and F prime be continuous maps from X to Y. They are given to be continuous. Then a homotopy between F and F prime, is actually a continuous map, is basically a continuous map. Let us denote that map by f is a continuous map from x times the interval 0 1 to the space y, such that when we restrict this f to point 0, we get this little f, and when we restrict this big F to 1, this is this little f prime. So this is true for all s in x. Note that this s is from the space x and this 0 is from this interval 0 1, and this 1 is from this interval 1. So in that case we say that this little f and little f prime are homotopic. Then f and f prime are said to be homotopic. The notation for this is f is homotopic to f. So this is the notation to represent f is homotopic with f prime. Let us consider an example. Let this space x be the closed unit interval 0 1, and this is equipped with some topology, say usual topology, and y be this topological space R and let f and f prime be the maps from 0 1 to R n. Then there is a homotopy. F from the space 0 1 times the interval 0 1 to R n, given as s and t, it goes to 1 minus t of fs plus t times f prime s. Note that this fs and f prime s, they are continuous, and hence this combination is also continuous. This implies that this f is continuous. Now it remains to show that when we restrict f to this 0, we must get this little f, and when we restrict this f to this 1 over here, we must get f prime s. Also f of s comma 0, this is same as f of s, and f of s comma 1, this is same as f prime s. So this implies that this f is homotopy. Now what happens geometrically? So suppose this is the topological space Rn. Now let this be the curve. So this is our curve f prime of s, and this is f, this is f prime, this is f. So this is our domain 0 1 cross 0 1. This is 0, this is 1, this is 1. So this is our domain. This is our domain 0 1 cross 0 1. Now during this homotopy, each point, say this point Fs, this travels along the line segment to this prime F prime S. This is point F prime S. So this point Fs travels along this line segment to F prime S. This is because the line through Fs and F prime S, this is linearly parameterized as f of s plus t times f prime s minus f of s, and which is same as 1 minus t times f of s plus t times f prime s. So with the segment from fs to f prime s covered by t values in the interval from 0 to 1. So now this interval over here 0 1, now these are the values s, and these are the values t. Now we have f of st. Now for each given t we get a continuous map. Actually this capital F, this is family of maps for different values of t. Now when we give t to be 0, so that means when t is 0 and s is free to vary over this interval. This interval over here, this is mapped to this map over here. And when we fix t to be equal to 1 and allow s to vary, we get this interval. This interval is mapped to this map over here, f prime. Now if we take another, suppose this is point t naught, then f of s comma t naught, f of s t naught, this will be mapped to some curve over here, say this curve. So actually this is a movie. When we move towards upwards, we get different curves. So actually there are infinitely many curves between these two curves. So if we consider a line segment over here like this, a vertical line segment, this vertical line segment is mapped to this vertical line segment. So for different intervals over here we get different maps between these two maps. So let us prove the following proposition. Homotopy is an equivalence relation. On the set C x y of set of all continuous maps from x to y. Let us prove this. Reflexivity. Now reflexivity is evident by the constant homotopy, that is define. Now what we have to prove? We have to prove suppose if we have this topological space x and y and there is a continuous map between them, say f, we have to prove f is homotopic to f, i.e. we have to provide a homotopy between f and itself. Define f from x cross 0 1 to x as f of st is f of s for all s in x and t in 0 1. So obviously f is given to be continuous. So when we restrict f to 0 we get f, and when we restrict f to 1 we get again f. This is a homotopy between f and itself. This is a homotopy between f and itself. Therefore f is homotopic to f for all f in C x y. Now as far as symmetry is concerned, suppose f is homotopic to suppose f is homotopic to G via the homotopy f, where this f and G, these are continuous maps from x to y. We have to exhibit a homotopy, say capital G, which will prove that G is homotopic to f. Therefore now f is given to be a homotopy between f and G. Therefore when we restrict f to 0 we get this little f, and on restricting this big F to 1 we get little g. Define another map. Define G from x cross 0 1 to y as G of st is same as G of f of s t minus 1. Since f is continuous, it implies g is continuous. Then g of s0, that means when we restrict g to 0, we get f of s1, which is by definition g, and g of s1, that is equal to f of s0, and by definition that is f. This implies, hence g is homotopic to f. Now it remains to prove the transitivity. Let f is homotopic to g, let f, g and h belong to cxy such that f is homotopic to g and g is homotopic to h via the homotopies, capital F and capital G respectively. Therefore, when we restrict f to 0, we get little f, and f restricted on 1, we get g. Similarly, and g restricted on 0, we get g, and g restricted on 1, we get h. We have to exhibit another homotopy which will prove that f is homotopic to h. Define h from x cross 0 1 to y as h of s t. Now this t belongs to 0 1 and s belongs to x. This is equal to f of s comma 2t. Now since this 2t belongs to 0 1, this 2t belongs to 0 1, that means 2t is less or equal to 1 is less or equal to 0, or 0 is less or equal to t is less or equal to half. So the condition for t is that it belongs to the interval 0 to half, and this is g of s of 2t minus 1. Again this 2t minus 1, this belongs to the interval 0 1, so 0 is less or equal to 2t minus 1 is less or equal to 1, or 1 is less or equal to 2t is less or equal to 2, or half is less or equal to t is less or equal to 1. So this implies this t has to be in the interval from half to 1. Now what it does, here we have this is my F, this is G, and this is H. Now from F to G we have the homotopy capital F, and from G to H we have the homotopy G. Now this F goes to G via the homotopy F in the interval 0, 1, and this G goes to H via the homotopy G in from time t, in time t, where t is in the interval 0, 1. Now we have exhibited here this homotopy H. Now what this homotopy does, it takes F to G in this half interval and G to H in the next half interval. So finally H takes this F to H in the complete interval 0, 1. Now note that F is continuous, G is continuous. To prove H is continuous, it is suffices to prove H is continuous at the point half. Note that H is continuous since limit t goes to left hand limit t goes to minus half of h of st, that is same as limit t goes to, let us keep here, this is less, t goes to half. Now when t is half, we have this homotopy here, this is f of s of 2t. So this is f of s of 1, and that is G. Similarly, limit t goes to half plus, i.e. the right hand side limit, h of s t. This is same as limit t goes to half. Now when t succeeds half, when t becomes bigger than half, we have this homotopy G over here. So this is G of s of 2t minus 1. So this is G of s0, and that is again this little g. So H is continuous at 1/2 as well, hence H is continuous. Also H of s0, that is same as f of s0, that is little f, and H of s1, that is G of s1, that is this H. This implies F is homotopic to H via the homotopy capital H.